So the update rule of Perceptron is as a very simple update rule. It just says that Wt plus 1 is Wt plus xi yi if mistake. Now there are two different ways you can make a mistake, right? So what are these two different ways your current Wt can go wrong on a data point? Well, pause and think about this. It's nothing too hard to see. I am going to say what these two types of mistakes. Mistake type 1 is when the algorithm predicts the label as 1, but then the actual label is minus 1, right. So, which means that predicted, let us say predicted is 1, actual is minus 1. What do I mean by predicted is 1, actual is minus 1? Well, this just means that sign of Wt transpose xi is greater than or equal to 0, but yi is minus 1, right. So, you had a current Wt, you had a current Wt and you find an xi yi pair where it is making a mistake. Why is it making a mistake? Because with respect to Wt, I am predicting 1. When will I predict 1? When I see that xi falls on one side of Wt, right. So, the positive side of Wt or the non-negative side of Wt, which means that sign of Wt transpose xi is greater than or equal to 0. But because it is a mistake, yi should have been minus 1, right. So, that is mistake type 1. Of course, mistake type 2 is just a symmetric opposite of this. Yeah, so here predicted is minus 1, but the actual is plus 1, right. So, why is the predicted minus 1? Because sign of Wt transpose xi was less than 0, but actual yi is plus 1, right. So, the opposite condition happened. Both of these are mistakes, right. So, but then the update rule is the same for both these mistakes. So, we need to justify why both these mistakes, why the update rule makes sense in both these cases. Okay. So, let us analyze mistake 1, right. So, let us look at mistake type 1. Type 1 mistake is when I am predicting, the algorithm is predicting 1, but then the actual point, the label says minus 1. Right. So, you had a Wt where this condition happened, Wt transpose xi is positive, well, I should not say sign here, right. So, it is just a sign is plus 1 or Wt transpose xi is greater than 0, yeah, Wt transpose xi is greater than or equal to 0, but yi is minus 1, right. So, now I updated Wt plus 1 to Wt plus xi yi. This is my new Wt, right. So, I am believing that, well, the old W is no longer correct, here is a new W which is correct. So, now I should ask the question, well, I have updated my W to a new W, then how does this new W perform on the point where the old W was making a mistake? That is the natural thing to ask. Now, what do I mean by how does it perform on the point? How does it classify that point where the old W was making a mistake? Well, how can I find that? I need to look at the dot product of the new W with the same data point and see how that looks like, right. So, which means that I should look at W, okay, I should keep track of whether it is superscript or subscript, yeah. So, I should look at Wt plus 1 transpose xi, but by definition that is just Wt plus xi yi transpose xi, which is just Wt transpose xi plus yi into xi transpose xi, which is norm xi squared, right. Well, this is what the new W's dot product with the point where the old W made a mistake, right. So, but now in mistake number 1, type 1, this value is greater than or equal to 0. Norm of xi squared is always a positive quantity, right. So, this is going to be greater than or equal to 0. In fact, you can, yeah, you can simply assume that the data points are not all 0. So, this is going to be greater than 0, but because there is a mistake, this guy was minus 1, right. So, which means that this whole thing is negative, right. So, what does that mean? That means that earlier I was making a mistake because the previous W's dot product with xi was positive, whereas it should have been negative. Now, what I am saying is that the new W's dot product with xi is the previous W's dot product with xi minus something, right. So, you are subtracting out something from the old W's dot product. Well, the old W's was positive, so you are subtracting out something. That does not mean that the new W's dot product with xi immediately becomes, negative. We do not know that, but we know that it is moving in the right direction, Why? Because this is positive, it should have been negative, but it is positive. So, you are subtracting out something. So, it is getting slower and lower, right. So, at this point it is going in the correct direction that the dot product should be negative, right. So, at this point we are not saying it is correcting the mistake, but the W is moving in such a way that the mistake, I mean at least the dot product is going in the correct direction, right. So, that is what is happening here, and very similar thing will happen here as well, right. So, here also the second mistake type also Wt plus 1 transpose xi is Wt transpose xi plus yi into norm of xi squared, but now in this case, well, the first term is less than 0, whereas the second term is yi is plus 1 now, and so the second term is greater than 0. So, now also the new w's dot product with xi, you want it to be positive, the old w's dot product with xi was negative. What you are doing is you are adding a positive term to it, right. So, if it was initially negative, maybe minus 10, now I am adding, let us say plus 5, so it becomes minus 5. It's not at, you know, it's not at positive, but then it's getting closer and closer to being positive, right. So, that's the idea. So, basically what is happening is, you can say that, you know, the update rule is such that, now this argument says that the update rule is a reasonable rule, right. So, update rule pushes W in the right direction for xi, right. So, if the dot product is positive, but then it should have been negative, then you are subtracting out something. If the dot product is negative, but it should have been positive, you are adding something. So, the update rule is kind of moving our w's in the correct direction. It does not mean that it is fixing the problem, but it is at least moving in the correct direction. Now, this is a local discussion, right. So, what we are saying is that, well, I made a mistake in some point xi, yi, and I am asking the question, how does the new updated W work for this xi, yi, right. So, maybe you are lucky that the new xi, yi, it pushed in the right direction and it actually fixed the mistake of xi, yi also, right. So, maybe the old W was making a negative dot product, whereas it should have been making a positive dot product. So, you update the W and good for you, the new updated W is making a positive dot product, which means that we have corrected the mistake for xi, yi. But that does not mean that the mistake that I corrected here for this xi, yi is not affecting some other data point in my data set, which was earlier correct, but then because I made this change has now become incorrect, right. So, in other words, what I am saying is that this local update, fixing it locally, it is not at all clear that fixing it locally will actually, you know, is a good thing in the overall scheme of things, because fixing it locally might break something else for some other data point. That could potentially happen, right. So, can that really happen? Well, let's see an example to kind of understand this in action, right. So, let's say here is our data set. So, this is a simple example where I am going to put some points here. Maybe there are some points like this, and yeah, maybe there are some points like this, and maybe there are some points like this. So, this is my labeled data set that I have in my hand, and let us say currently I have a W like this. This is my, let us say, current W. Now, at some iteration I have this W, I have this labeled data set, and I ask the question, well, does this W make a mistake in my data set? Well, how do I check that? Well, I look at the line that this W corresponds to, which is this line, and now all the green points on the positive side and all the red points on the negative side? Well, almost, except one guy, right. So, except this point here, everybody else is correct, right. So, this is a point where I am making a mistake. So, which means that I need to update my W based on this point, right. So, now how will that update happen? Well, greens are positive, reds are negative, right. So, that's, let me make sure we write that. So, this is plus 1, red is minus 1. So, which means that now what would be the new W? Where is going to be the new W? Well, the new W is going to be Well, this is, if this is x, the corresponding label for this in my data set is green, which is 1. So, I am going to, my new w is going to w, current w plus x into 1. I am multiplying 1 because the label is 1, right. So, this is, let us say w, let me say this is w old, now w new is just w old plus x times 1, right. So, this 1 is just y, right. So, just a green point. So, where is, what does that mean, right. So, this is my, so let me plot the x point now, which looks like this. This is the direction of x, which means that I am going to add that to my old w, which if I am drawing it correctly, which will pull it, will put it somewhere here, right. So, this is going to be my w new, right. So, this is w new, which is w old plus this x, right. So, that is what it means to say I am adding x. Okay. So, now what has happened is my w has updated. So, let me look at the new w, which is, this is my new w, which is w new, and let us see how this w performs on my data set, right. So, how would this w perform on my data set? This would say anybody on this side is positive, anybody on the below this orange line is negative. Well, if you look at the point x, now this new w is saying x is positive, which means that I have fixed the problem for x. But have I fixed the general problem? Well, this has introduced new errors here, right. So, these guys were earlier correct with respect to the blue line, right. So, these were positive with respect to the blue line before for w old, but now w old has become w new, and so that the line has shifted, and because the line has shifted, these guys are all now mistakes, right. So, I tried to fix the mistake of x for w old, and so I came to w new. I fixed the mistake of w old for x, but then this w new is good for x, but then it is bad for a lot of other guys, right. So, which means that though the update rule is pushing correctly in the direction for the current point where you are making a mistake, it might introduce mistakes for other data points. So, it is not at all clear if this update rule is actually a solid update rule, right. So, and that is one of the reasons why this algorithm is surprising and surprisingly effective also. So, let's talk about more about you know, whether this is a good algorithm in the sense that this update rule, will it lead to a convergence, or you know, you might keep fixing local mistakes, but then introducing some other mistake somewhere else. Now, if I fix that mistake, some other mistake will again get created, and this will keep on going on forever, that I will never converge, right. So, one might argue that. So, if you are saying that the algorithm converges, then it means that we should say that this situation will never happen, right. So, that we need to kind of argue, which is what we are going to do now, right. So, but let me note down what is the problem that we saw here, and then we will go ahead and try to fix this, right. So, try to understand this better. You know, fixing w for 1x might affect decision for other data points. So, need more careful argument for convergence. This argument is, I mean, we have to be very careful when you are trying to argue convergence of this algorithm. Okay, so let's look at another example, which is another revealing example that will give us some insights into this working of this algorithm itself, which is in some sense a border case, right. So, it is like a corner case kind of an example, but it will give us something useful to understand. Okay, so here is another example, right. So, now let us say I have again a 2-dimensional data set, but this time the data set just has 3 points, right. So, I am going to put 2 points here. This is the point 0, 1, and it is labeled as +1, right. So, it is +1 and here is a point, another point which is 0, -1, and I am going to label this as -1. and I have a third point, let us say, which is somewhere here, which is minus 1.5 or half, and now this is labeled as minus 1, right. So, this is a negatively labeled point, the others are positively labeled. This is my data set, this is plus 1, sorry, yeah. So, I just have 3 data points, 2 data points are labeled plus 1, 1 data point is labeled minus 1, this is my data set, right. So, first question that I would like to ask you is this a linearly separable data set? So, just, I mean, this is a good thing to pause and think about, right. So, with respect to our definition of linear separability, is this a linearly separable data set? In other words, what I am asking is that, is there a W such that for the points labeled plus 1, W transpose X is greater than or equal to 0, and for points labeled minus 1, W transpose X is less than 0. If you can find such a W, then this is a linearly separable data set. If you cannot find any W, then this is not a linearly separable data set. So, is this a linearly separable data set? Pause and think about it, I will tell you the answer now, right. So, just to make sure, so this is our data set, right. So, 0 comma 1 comma plus 1, 0 minus 1 plus 1, minus 1 half, which is minus 1. This is our data set. So, is there a W in R2, this is a 2-dimensional W, such that W transpose Xi is greater than or equal to 0, implies Yi is plus 1, and W transpose Xi is less than or equal to for all Yi, which is minus 1, right. So, is there a W like this? Well, in fact, the answer to this question is yes, there is a W. What is that W? Well, that W is just, any W that is pointing along the positive x axis. Now, if I take this W, let us say this is my W, right. So, now with respect to this W, my separator is just the y axis, which means that for these 2 points which lie on the y axis, W transpose X is 0, which satisfies W transpose X is greater than or equal to 0. So, the label has to be 1, which in fact is 1 in this case. And for the point which is on the other side of the y axis, W transpose X is negative, and so the label is also minus 1. So, this is a linearly separable data set according to the definition that we put down. So, now what we want to ask is, what does, so let us say I give Perceptron this data set, just 3 points, and see what Perceptron's algorithm does in the way that we have put down the algorithm, right. So, it's instructive to, go through this example so that we understand what is happening with this algorithm, right. So, let me draw this again, so here is my data point, which is plus 1, this is plus 1, this is minus 1, this is 0 1, 0 minus 1, and this is minus 1 half. So, what does Perceptron do? Well, Perceptron, how does Perceptron work on this data set? It's going to start with W naught, which is just 0 0, right. So, this is a 2-dimensional vector. By our algorithm's initialization, it's going to be 0 0. Now, what will it do? Well, what does 0 0 mean? Well, so let us call this points x1, x2 and x3, so that we can keep referring to them easily. So, W naught transpose x1 is 0, W naught transpose x2 is also 0, and W naught transpose x3 is also 0, because W naught is 0, it is going to make a 0 dot product with everybody. So, which means that for the W naught, my predicted y is y1 is plus 1, predicted y hat 2 is also plus 1, and predicted y hat 3 is also plus 1, right. So, because the value is 0, if it is greater than or equal to 0, my sign function is going to say the label is plus 1, right. So, in this case all 3 would be predicted plus 1. So, which means I have gotten 2 points correctly out of 3. and the point where I make a mistake for this with respect to this w is x3, which is this point, right. So, which means my w1 is just going to be w0 plus x3 into y3, because that is the point where I make the mistake in my data set, which is just 0 0, which is my w0 plus x3 is minus 1 half, and what is y3? Well, y3 is just y3 in this case is the label of x3, which is minus 1. So, that is minus 1. So, my new w is going to be 1 times half, 1 times minus half, right. So, which is where is the new w? Well, my new w is going to be pointing in this direction, right. So, this is 1 minus half, this is my w1, right. So, which means that visually we can see that, so everybody on the below this diagonal orange line is going to be labeled +1 and above is going to be labeled -1. So, now we ask the question, is this w correctly classifying all my data points? Well, almost, except that it is incorrectly classifying x1. x1 is a mistake. It is correctly classifying x2 because it is on below the diagonal orange line. It is correctly classifying x3 because it is above the diagonal orange line, but then x1 is above, but it is labeled +1, which is a mistake, right. So, which means that now I am going to update my w using x1, right. So, which means my w2 is going to be w1 plus x1 y1. Well, what is w1? 1 minus half plus what is x1? x1 is 0 1 times what is the label of x1, which is 1. Now, what would this give me? Well, this is going to give me 1 plus 0, which is 1, minus half plus 1, which is half, right. So, this is going to give me 1 half, right. So, that is going to be my w2. Well, where is w2? Well, if you look at where w2 is, let me plot it using blue. Well, it is going to be 1 half, right. So, it will be somewhere here. This is 1 half, which is my w2, which means that the corresponding line is going to be like this, right. So, everybody on the right hand side of this diagonal blue line is positive, on the other side is negative, right. Again, you see that it is classifying x1 and x3 correctly now, but x2 is incorrectly classified. So, which means that Perceptron will make one more update, and it will, let us put that here, and that update will get me w3 as w2 plus the mistake is with respect to x2, which means that x2 y2 has to be added. What is w2? w2 is 1 half plus x2 in this case is 0 minus 1. What is the label corresponding to x2, which is 1. So, now the new updated thing would be 1 plus 0 1 half plus minus 1, which is minus half. Well, w3 is 1 minus half, but we know this is also same as w1, right. So, which was also 1 minus half. So, what is happening now is that, well, we were at w0, which is 0 0, from which we got w1 and we went to w2, and now again we are coming back to w1. Now, we know that both w1 and w2 are not optimal for this data set. So, that it makes one mistake each, but then what will happen is you will keep switching between w1 and w2 and the algorithm will never converge. So, what does this tell us? This tells us that this tells us something interesting about the algorithm itself, right. So, we started with a data set which for which according to our definition is linearly separable, and now we try to run our Perceptron algorithm, right. So, our goal was to see if Perceptron algorithm will get us a w if the data set is linearly converged. If the data set is linearly separable, will the algorithm give us a w which correctly classifies all our data points? But now it looks like that is not the case, because we started with a data set which is linearly separable, though it had just 3 points, nevertheless it is still a data set, and according to our definition it is linearly separable. But if I run the Perceptron algorithm, it is not going to get me a w which correctly classifies all my data points. In fact, what would happen is Perceptron algorithm will never converge. It will keep jumping between w1 and w2 and it will never converge, right. So, that means that we cannot say that if your data set is linearly separable, then Perceptron algorithm will converge, right. So, that is not good enough, right. So, that is the problem here. That is the problem that I am going to kind of say here. No, but that is, so then one can ask, why did this happen, right. So, why are we though the data set is linearly separable, why did this algorithm fail to converge? Is it like, there is something special about this data set which was carefully picked that made perceptron not converge, or in general perceptron itself is a bad algorithm, it will never converge, right? So we can ask that question. And if you think about that, right, so one of the properties of this data set is that we said that it's linearly separable, but in some sense, it's strictly linearly separable, right? So well, it's not strictly linearly separable, I should say. The reason I say that is that it's linearly separable, but then we are using the fact that there are points on the boundary, on the decision boundary, and for which W transpose X is 0, and we arbitrarily decided to say that W transpose X equals 0 means that the label is +1. That's because that's how we define the sign function, right? So, but then if the points are on the decision boundary, and it's a corner case in some sense, right? So because it can either be labeled as +1 or -1, but then we chose to do it as +1, and because of this arbitrariness of labeling points on the decision boundary, somehow that is affecting the convergence of perceptron algorithm. So then we can ask the question, well, if this is our definition of linear separability, then perceptron is not going to give us convergence always. So can I make a slightly more restriction on my data set and ask, well, if I assume something more than just linear separability, I will also assume that with respect to that optimal W that actually classifies my positives and the negatives, no point should actually lie on the separator itself, right? So we can make such an assumption and then ask whether perceptron will converge or not, right? So what do I mean by that? So let's make our assumption that we want perceptron, that we want to assume where perceptron will work well, more precise, right? So let's make that assumption precise. So here is the assumption. This assumption is a very fundamental assumption and it's called linear separability. Well, we are saying that the data set is going to be linearly separable. So it is linear separability, but then with a twist, right? So with gamma margin. Now this is the assumption that I am going to make, right? So what does it mean to say linear separability with gamma margin? Well, it means in pictures, it means the following, right? So you have a data set in 2 dimension again. Now again I am labeling some points as positive, some points as negative, let's say things like this, maybe like this. And now what is happening is, I have, this is a linearly separable data set obviously, because I can draw a W like this such that this line separates the positives from the negatives. Maybe I'll remove this. So now it's not just linearly separable, it's also linearly separable with gamma margin. What does that mean? That means that if I can draw these lines which are parallel to the separator, I'm just going to adjust my point so that I can make my comment very clear. Maybe that's a point here, right? So now what we are saying is that you have a data set. Now this is the W for which this line is W transpose X equal to 0, right? So this is the set of all X such that W transpose X equal to 0. Now what we are saying is that there are no points that will lie on this line in my data set. For there is a W which will separate my positives from the negatives such that there are no points that lie on the line. Which is one more way of saying that is to say that, well, I can look at these 2 lines which are parallel to the line that passes through the origin. This is the set of all X such that W transpose X equal to some gamma, maybe gamma is 5, which is 5 units away parallelly. I have moved my separator on the positive side, and this is the set of all X such that W transpose X equal to minus gamma. Now what does this assumption essentially mean? Well, it means that I will not get any point in the space between these two parallel lines, right. In other words, I am saying that the data set is such that there is a W such that this W classifies the positives from the negatives correctly, and just not classifies it correctly, it classifies it with some gap, right. So, some margin. So, let me make this assumption in precise, right. So, we are going to say a data set which is just a bunch of x1 y1 till xn yn as usual is linearly separable with gamma margin if there is some W star in RD such that W star transpose Xi, and the way I am going to write this is into Yi is greater than or equal to gamma for all I for some gamma which is greater than 0, right. So, this is the definition. So, it needs some parsing and we will do that now. So, basically what I am saying is that you are given a data set. Now, there is some W star, right. So, we are assuming that there exists a W star such that with respect to this W star, if I try to find W star transpose Xi and multiply it by Yi, then this product should be greater than or equal to some positive quantity gamma. The gamma cannot be 0, right. So, the gamma is a positive quantity. Think of this as 0.1 still okay, 5 is still okay, 100 is still okay, right. So, it cannot be 0, it has to be some positive quantity, right. So, what I am saying is that there is a W star such that this W star has the property that W star transpose Xi into Yi is greater than or equal to some strictly positive quantity. Now, why am I doing this product W star transpose Xi into Yi? Well, this is a compact way of saying that if Yi is 1, then this is saying that for all the points which are labeled 1, W star transpose Xi is greater than or equal to gamma, which means that all the points which are labeled plus 1 have the property that they are, oops, sorry about that, they are on this side, right. Now, this side, when I say this side, it includes this dotted line, right. So, the dotted line and everybody on the other side, right. So, this is the set where W star transpose Xi is greater than or equal to gamma, right. So, and now when I multiply it by Yi, right. So, which means that whenever Yi is 1, it better be in this yellow shaded region, and whenever Yi is minus 1, which means W star transpose Xi into minus 1 is greater than or equal to gamma. Equivalently, W star transpose Xi is less than or equal to minus gamma, which means that all the points which are labeled minus 1 in my data set must then have the property that they are on this side of the, right. So, they are on this side. Of course, this also includes this line W star transpose X equals minus gamma, right. So, now this leaves this in between region, right. So, this region, there is no point in my data set in this region, right. So, this is the assumption that we are making, which means that in particular there is no point on the line W star transpose X equals 0. That is no point in my data set satisfies W star transpose X equal to 0. Now, I am not assuming anything about how big or small this gamma is, right. So, I am just assuming that there is some gamma which is positive. Gamma cannot be 0, which means that this gap could be as small as possible, but then we are saying that the gap cannot be 0. That means that no point can lie on the separating line itself, right. So, this is what we will call as linear separability, but then with this extra small mild condition that there should be a gamma margin. Now, which means that if we are making this assumption on our data, then well, it means the previous bad data set that we had, which just had 3 points, is disallowed, right. So, we are saying that we will not see such a data set in our data, right. So, this data set is not allowed under our model. Our model only assumes linear separability with gamma margin. However small gamma can be, it is going to have this assumption. So, this is assumption, right? So, this is the main assumption, and we are going to work with this assumption and to see how this assumption can help us provide a proof of convergence for the perceptron algorithm, right? So, this is one of the first algorithm which had a a proof for its convergence under this assumption, and so it makes sense to go over this proof and understand what are the important elements of proving this, and the reason why I want to do this proof in this course is because this proof will reveal something interesting about the dependence on the relevant quantities that make up a problem, which will lead us to more stronger algorithms later in this course, right? So for that purpose, I will go ahead and do this proof just for us to get a sense for how can we argue that perceptron actually converges when we put down this small mild extra condition, that linear separability with gamma margin.